This is Brute Forsyth, my extrusion force testing machine. It works by measuring the force required to push plastic through a 3D printed hot end. In the last couple of episodes, we've been taking a look at extruders and dual extrusion and how that stuff kind of works relative to one another. But today we're moving back to hot ends, as Slice Engineering has sent me this, the Mosquito Magnum Plus, an all metal, high temperature, 100 watt dual thermistor $400 hot end. And I'm going to put it through its paces to find out how good it is. The maximum speed at which you can print on an FDM machine is typically limited by just one factor, and that is how fast you can push plastic out of the hot end, which we call flow rate. The higher the maximum flow rate of the hot end, the faster we'll be able to print. The way I'm going to find out what the maximum flow rate is by measuring the force required to achieve various flow rates. Although there are many factors which influence how much force it takes to push plastic out of a hot end, most of which are as a result of friction, like even rotating the spool on a spool holder, there are two main properties which determine the majority of that force, and those are viscosity and geometry. The first property, viscosity, is a measure of how thick and gloopy a fluid is. This is, in simple terms, impacted by the material which you're using, like PLA, PETG, ABS, etc., and the temperature at which it is. The lower the temperature, the more viscous the filament. The higher the temperature, the less viscous. So low temperature requires more force, higher temperature requires less force. The second property is geometry. Now that's all down to the design of the hot end. The materials used, the roughness, tolerances, and probably most critically, the nozzle diameter and throat steepness can all be restrictive of the flow. So the more restriction in the design, the higher the force required to extrude. From those two things, you can probably see how by measuring the force as we do extrusion, we can get an idea of how viscous the filament is and about the design of the hot end, and therefore determine performance of that system. I chose the 100 watt and dual thermistor version of the Magnum Plus, which is pretty much the top spec version, and it was pre-assembled for me, which was nice, so I didn't really have to do much other than insert the nozzle. The first challenge with wiring up this hot end is that it has two thermistors. Now, most firmwares don't actually support the use of two thermistors to control one heater, so the way I have it set up is that one thermistor controls the heater and the other one is just sort of like a thermal switch. If it goes over a certain temperature, at which point we know the other thermistor has probably failed, it will just turn everything off. The other setup challenge is what to do with the dual heaters. Obviously you can put either two heaters onto a single output, wiring them in parallel so they both get 24 volts or whatever voltage and maximum power, or you can put onto two individual outputs. The advantage of using a single output is most of the control system then just works exactly the same as before. The downside is that you do have to be very careful to make sure that the control board is rated for the current draw that you get at your voltage and 100 watts. However, the downside of these two single outputs is that the controlling is a little bit more complicated. RetRap firmware doesn't like that control via a dashboard. It has to be via G-code. So for me doing testing, it was a little bit of a pain to do that. So I went with the single output version, which is fine for the Duet 2 Wi-Fi because it can carry the amount of current needed for 100 watts and 24 volts. So on to the testing. For the extruder, I'm using an E3D Titan, and the materials I've tested are PLA, PETG and ABS at 220, 250 and 260 degrees Celsius. Yes, these temperatures are deliberately on the warm side. I've also used three separate Slice Engineering Bridgemaster nozzles, which are 0.4, 0.8 and 1 millimeters. The 1 millimeter nozzle was provided by Slice Engineering with the hot end, and I purchased the other two myself. I don't have a 0.6 millimeter nozzle, unfortunately. I was after one, but I don't think they were in stock or something at the time. Probably should have asked Slice Engineering at the time that they sent it, but I didn't. So anyway, there's no 0.6 millimeter nozzle. In terms of the actual test procedure that we're going to be running through today, it is a little bit different to what I've done before because I've done some testing between the last video and this that indicates that extrusion does not settle within about 45 seconds. So our test has got to be 45 seconds long in order to make sure that everything is kind of stable. So what we're going to do is start at 2 millimeters cubed per second and increase every 45 seconds by 2 millimeters cubed per second, all the way up to 100 millimeters cubed per second. But the test will stop at any point if the filament stops moving, the extruder just doesn't push anything anymore and nothing's happening. Between the 45-second test, there is a 50 millisecond gap, and this is just long enough so we can disable one test and start the next, and the kind of computer stuff can log that that has happened, so we can count our tests and log them properly. That's it for all the setup and preamble. Now let's dive into the results and let me explain it step by step. There's a lot to cover, but it's super duper interesting. So let's start with this single run of the PLA 0.4mm nozzle with a 50 watt heater. So for 50 watts, that's one of the two heaters, the other is disabled. So every line color is a different flow rate, although obviously some colors are quite similar. You can see starting from the bottom, it's all quite low force really and fairly steady, with the exception of the starting forces, which is like the start of each test. As we go up the chart, the flow rates and forces are both increasing. In the high force regions, so at the top of the graph, you can see where there is some repeated skipping and also the test where the filament stopped moving. So the test was obviously aborted and you can see where that stops as well. If I filter out the tests that kind of scribble over thing due to skipping, which we know are not practical for actually printing anyway, we can get a really nice looking graph. This is just one of 3 repetitions of the test for one material at one nozzle size. So there are many more data sets just like this one. The other thing I want to point out is that you can see how the lines are close together at the bottom, which means less force is needed to increase the flow rate, while they spread out towards the top, which means more force is needed for the same increase in flow rate. Lastly, the lines are much more wobbly or vary a lot more at higher forces, suggesting that the flow is less consistent, so the force is varying more. This will be important later on, just so you remember what that looks like. So to start summarizing, let's look at the average force for each flow rate. So to work this out, we first cut off the first 5 seconds to get rid of that first initial startup effect, and then calculate the mean for the remaining 40 seconds of each flow rate separately. We then plot this as a single line of average force against flow rate. Let's also include the averages for the other 2 runs that use identical parameters so we can see how consistent the results are between these 3 tests. This looks fantastic already, but let's chop off anything where the force is lower than the previous test, as the test is ended at this point, so the results are no longer relevant. Now we can start to pick this apart. The data appears to be split into 2 segments. A lower linear section with flow rates up to around 25 millimeters cubed per second and forces up to around 2,000 grams, and an upper section which is also linear and covers the remaining forces and flow rates. We also have this transition period in the middle. The run-to-run variance in the lower part of the test is minimal, around 3%, while run 2 is different to 1 and 3 in the upper section and varies by around 8%. I'm pretty happy that these results are close enough. 8% is quite a bit, but hopefully not too bad. So let's average them into one line and add in standard deviation and the relative filament extrusion percentage so we can see how that affects our view of the results. Here we have the average force in orange, and that uses the vertical axis on the left, the standard deviation in dark blue using the right-hand side axis, and the percentage of filament flow in green, also using the right-hand side axis. Standard deviation we've covered before, but the percentage of filament flow is basically calculated on the total filament extruded for the test compared to how much should have been extruded ideally. This is represented here as a percentage, so anything more than 100% means over-extruded and less than 100% means under-extruded. I've used a modified version of the Polygono filament sensor, which you won't have heard of because although it was a product I was lucky enough to test a little while ago, unfortunately it never made it to market, but I get to use it here, so this is pretty good. What we're seeing here again seems to be 2 segments. A stable section that is quite consistent, and then a second part where the deviation significantly increases. From this, my hypothesis is that while the standard deviation remains low, say 35 grams, the flow quality remains high, and the hot end is performing ideally as intended. When the standard deviation is greater than this amount, again say 35 grams, the system is reaching a flow capability in some capacity. For this test, the 35 grams of standard deviation corresponds to a peak flow rate of 28 millimeters cubed per second and 97% of maximum flow rate. If we look near the end of the test at 40 millimeters cubed per second, we can see the deviation is up to 65 grams and the extrusion is down to just 85% of what it should be. As a quick side note, you'll often see quite a bit of variation in the first test. This is because I didn't have a purge system at the beginning of the test, so I often used the first test as a manual feed to make sure everything was running normally, and we started at 0 force. So the first test you can just basically ignore, although I will be showing it most of the time. If we look at the same graph we just saw, but for a 0.8 millimeter nozzle, this is what we get. The transition portion of the line for average forces is slightly less obvious, and it starts to look a lot closer to a gradual curve. The run-to-run variation is slightly higher, so this is a potential source, but even the raw data shows a much less sharp transition than we saw with the 0.4 millimeter nozzle. In a rather satisfying way though, we do still see a sharp increase in standard deviation around the same time as the change from one linear segment to the other in this transition zone. In this case, this transition is around a standard deviation of 50 grams, which corresponds to about 97% flow at 46 millimeters cubed per second. Looking at the same graph again, but this time for a 1 millimeter nozzle, we get this. Again, the transition portion is less obvious, but certainly still apparent. For the standard deviation, we see a sharp increase around the transition point. In this case, it's slightly higher again at around 60 grams, which corresponds to about 95% flow at 46 millimeters cubed per second. This time, 97% flow is almost exactly 50 grams at 36 millimeters cubed per second. The last graph for PLA is for a 1 millimeter nozzle again, but this time for 100 watts instead of all the other tests we've seen so far, which were 50 watts. While we see similar patterns in the extrusion percentage and average force, the standard deviation is all over the place. For some reason, the 1 millimeter nozzle at this higher power really struggles to keep a consistent force. Transition starts around 40 grams and 42 millimeters cubed per second. So what's my conclusions on these PLA tests? Well, firstly, I want to preface my conclusions and results with a slight change in terminology. In nearly every case, hotends are marketed and sold on the basis of their maximum flow rate. I think personally this is a bit daft because there isn't really a maximum. You just push harder, raise temperatures, and the filament will come out. It's like there is no point where it stops. What I want to specify, and I hope catches on a little bit more, is an optimum flow rate. So this would be the fastest flow rate you can achieve whilst maintaining a high quality and consistent flow. You can push faster, you can push harder, but with the downsides of reduced extrusion quality. So what is the optimum flow rate for the Mosquito Magnum Plus with PLA for these three nozzles? The criteria I've used is less than or equal to 3% loss of flow rate. It must remain within the first linear section or early in the transition section, and must be before any spikes in standard deviation. And this is what I found. As you might expect, the 0.4 millimeter nozzle and 50 watt heater has the highest and thus worst force per unit of flow rate gradient and the lowest optimum flow rate. Being low power and highly restrictive, this is pretty much to be expected. The 0.8mm nozzle performs the best of the bunch, achieving the best flow rate at 46 millimeters cubed per second and the lowest force per unit flow rate. Where it gets confusing is the 1mm nozzle. This should be less restrictive than the 0.8mm nozzle, but with a 50 watt heater, it requires almost the same force as the 0.4mm nozzle, but does achieve a better flow rate of 40 millimeters cubed per second, meaning it was a bit more stable. I thought that this could be a problem with insufficient heat. Maybe the larger nozzle needs more power, which seems true to some extent as the 100 watt heating improved the force per unit flow and optimum flow rates, but not enough to catch up to the 0.8mm nozzle. I know it just looks like I've confused the nozzles and got them the wrong way around, but I double checked the writing on the nozzle. I tested multiple times to make sure the results were the same. I promise you, this is what I got. Also, don't forget to click that subscribe button for more in-depth extrusion testing like this. For now, let's get on with the ABS testing. So all the ABS testing was done at 100 watts, and this is the 0.4mm nozzle. The average force does seem to just about still have the bilinear shape, meaning two linear sections with the transition zone in the middle. The transition zone is very wide though, giving a very gradual curve. The standard deviation seems to climb significantly even from a very low flow rate. It stays below the 30 to 40 gram region until about 12 to 15 millimeters cubed per second, but then jumps up to 60 and then just goes crazy. While PLA was pretty well calibrated, the same settings for ABS are resulting in about 97% of the expected flow right from the start. A 3% decrease from that point, around 94%, corresponds to 30 millimeters cubed per second and 76 grams of standard deviation. It's a very similar story for the 0.8 millimeter nozzle. The standard deviation is low, up to around 26 millimeters cubed per second this time, but then jumps up to over 100. 3% drop in flow rate occurs at 44 millimeters cubed per second and 140 grams of standard deviation. For the 1 millimeter nozzle, we get low deviation up to around 20 millimeters cubed per second before it jumps to over 60. On first inspection of the 0.8 and 1 millimeter nozzles this time, it looks like 0.8 does better since the standard deviation remains low up to higher flow rate, but then moving to flow rates beyond this point, the 1 millimeter nozzle does seem to remain more consistent, while the 0.8 millimeter nozzle has pretty large peaks and seems a little bit unstable. But then again, are we beyond the limits of the nozzle anyway? So does it matter at that point? The summary for my results in ABS is a little bit more difficult because the standard deviation seems to increase much sooner than I expected. So I was wondering if maybe we should change the requirements, but no, we're sticking to the same. But I do want to clarify, as before, I'm classifying these as optimum flow rates, not maximum flow rates, because I don't really think there's a maximum. So, as with PLA, the 0.4 millimeter nozzle performed as expected with the highest force per unit flow rate and the lowest optimum flow rate. The 0.8 millimeter nozzle performed the best again, nearly doubling the optimum flow rate compared to the 0.4 millimeter nozzle with around 2/3 of the force gradient, leaving the 1 millimeter nozzle with force and optimum flow rate splitting the difference between the 0.4 and 0.8 millimeter nozzles. Now let's look at PETG with a 1 millimeter nozzle. We seem to be completely losing this bilinear average force that we saw with ABS and PLA, and instead there's just a really gradual curve. The standard deviation also climbs very gradually over the course of the test, as opposed to the sudden jumps that were observed with both ABS and PLA. I can only presume that this is simply down to different material properties and how it flows under pressure. It starts to look like maybe we didn't reach our maximum flow rate in this hot end testing because we didn't get that kind of spikes and jumps that we were expecting, but we did definitely reach the hot end maximum capacity, in case you're wondering, because the flow output started to look like this weird bobbled pattern that definitely would have been super weird to see in a print. And of course, the extrusion quantity dropped to 80% of what it should have been. I've only done a 1 millimeter nozzle test for PETG, so instead of what we did before, we'll instead use this to compare across different materials with a single nozzle size and the same power. Again, I was looking for this 3% loss of flow rate for characterizing general performance, but without any obvious climbs, jumps in standard deviation, or going outside of that transition area. This was definitely more difficult with PETG because we had that gradual curve though, so I'm a little bit less confident in the results here. So in this material versus material test, things are not quite as I expected. ABS and PLA both achieve the lowest force per unit flow rate and are also within spitting distance of one another, very, very close. That being said, PLA was able to achieve more than twice the flow rate while maintaining the critical low deviation and high relative flow. PETG was pretty confusing, but we can be sure that the force per unit flow is almost double that for ABS and PLA, although it seems to be a bit more stable than ABS as we managed to achieve a 38 millimeter per second optimum flow rate. Obviously there's another dimension to these test results though, and that is temperature. I've only tested everything at a single temperature, so that could be why we're seeing an advantage for PLA here, as its relative temperature to what it maybe normally is printed at is higher than compared to ABS or PETG. Okay, so what can we actually learn from all of this testing? What's the point? In general, we can definitely say that ABS, PLA and PETG are really quite different. PETG especially, I think. And I think we're all aware of that in terms of mechanical properties and finished parts. We know that they respond differently to forces in different ways. But now we're seeing a really big difference in the way they heat, in the way they extrude. They all just responded really quite differently to very similar input parameters. The second thing is that I think we need to start looking at flow compensation for high printing speed. As the flow rates and therefore speeds increase, forces increase, and as the force increases, the kind of relative extrusion drops. If we could compensate by kind of targeting over extrusion so that the actual extrusion is where it should be, I think this could potentially improve print quality through a single print where flow rates are changing for different speeds depending on which features are being printed. It won't necessarily help us print any faster, but it should at least improve that consistency throughout a print. But what about more specifically? What are the effects of heating and the materials and nozzles on the performance of the Magnum Plus? I only have results for PLA when it comes to 50 watts and 100 watts using a 1mm nozzle. So for these circumstances, this doubling in available thermal power increased the optimum flow rate by 10% and reduced the force required by 18%. A quite small but definitely not insignificant amount. Perhaps the 50 watt cartridge is reaching somewhere near a limit, but the additional thermal distribution by having two cartridges may have also impacted that improvement. Studying the impact that the change in material had on the performance was also pretty interesting. Many speed benches are printed in ABS, and one reason for this is that it doesn't require as much cooling in order to sort of retain its shape during printing. But I had the impression that it also melted much more easily and flows well at high speeds. However, my testing today indicates that while PLA and ABS would both be limited by the extruder at the same time due to their similar force per flow gradient, if provided enough force and cooling, PLA would be able to, in theory, print faster than ABS. PETG remains the biggest puzzle, as I didn't do as many tests with PETG, so I'm not really able to make any strong conclusions on that yet. Perhaps the most surprising result, though, is not that PLA can print faster than ABS, but that the 1mm nozzle did not perform better than the 0.8mm nozzle. I don't know if there's some different internal geometry in that 1mm nozzle that's the Bridgemaster type, but personally, I feel like I've done enough repetition to conclude that the 0.8mm nozzle for printing faster is a better choice than the 1mm nozzle. That's definitely the one I'd go for, given this information. I think it would be a missed opportunity though now for me to not talk about peak flow rates. Other than the limits of extruder force and poor consistency of melting through the cross-section of the filament, I don't see any evidence that there is a maximum flow rate for a hot end. Maybe there is, but it's far beyond the capabilities of what I was able to test. And trust me, I did extrude far into regions where filament artifacts start to be so significant that you just wouldn't want to print with that. So personally, I think hot end maximum flow rates are kind of a bit of a myth. So for the numbers I've used today, again, please remember that these numbers are calculated probably quite a bit differently to how everyone else has quoted numbers. One thing I would like to be more widely adopted is a more variable independent parameters for investigation. So this force per unit of flow rate would basically enable us to compare different hot ends independent of an extruder. Different extruders are capable of different forces. But if you don't have that force information, how can you possibly identify the maximum flow rate for a hot end? Because it depends on the force you can apply. So again, there is no real maximum. It all just depends on what you have installed, what temperatures and what materials you're using. So to round this off, this graph is all the flow rates I'd recommend for these nozzles, materials and temperatures that I've tested today. Hopefully that's useful for anyone looking to get this hot end. You can find a link if you want one down below. Thanks very much for watching, and I'll see you in the next one.